Welcome to this second lecture in the introductory lecture on fundamentals of transport processes. As I had said in the last lecture, in transport processes we shall be considering material transformations, transformations from raw materials to finished products, and the objective is to do it in a repeatable, efficient, economical, environmentally friendly manner. And transformations are of two types, physical and chemical. Here we shall mostly be interested in transformations in fluid phase, because as I said, in a fluid molecules do not have fixed locations. They move due to thermal motion, they move over around the entire liquid, and because of that it is possible to effect transport of materials relative to each other, which is required for material transformations. Okay, require materials to move relative to each other in order to effect material transformations, and therefore these are mostly carried out in fluids, that is liquids and gases, because the time scales required for transport of materials relative to each other in solids is much longer than industrial time scales typically. Okay. Therefore, we shall consider liquids and gases. The fundamental difference between liquids and gases is the spacing of the molecules. In liquids, the molecules are approximately 1 molecular diameter apart, and therefore they are densely packed, and nevertheless the molecules do not have permanent fixed locations. They diffuse throughout the liquid, and because of that it is possible to move materials relative to each other. That is, motion of materials relative to each other requires motion of the molecules of those materials relative to each other. In gases, the distance between molecules is approximately 10 times the molecular diameter, and molecules interact due to instantaneous collisions in the kinetic theory of gases. The time of an interaction between molecules is much smaller than the time between interactions of molecules. Okay. So, here we shall look at transformations in fluids, and I had explained to you why we need to look at transformations. Okay. So, we took the example of a stirred tank reactor, where a reaction takes place at a catalyst surface. You pump in the reactant, you pump out the product, and you provide sufficient heat for the transformation to take place. That is not enough. You need to make sure that there is sufficient transport of reactant to the surface of the catalyst where the reaction is taking place, sufficient transport of product from the surface where the reaction is taking place, sufficient transport of heat to the surface in case of endothermic reactions, or sufficient transport of heat from the surface of exothermic reactions. And all of these transport rates are related to the variational properties between the surface and the bulk. The mass transport is related to variations in concentration, heat transport to variations in temperature. Okay. And similarly, when you stir the fluid in the reactor, the resistive force to the motion of an impeller relative to the fluid is due to the momentum transport to the surface. You need to be able to predict the rate of momentum transport due to the difference in velocity between the fluid and the surface in order to predict how much power is required. Okay. Similarly, for the case of a heat exchanger, the heat transport across the surface is due to the temperature difference across the surface, but the heat transfer along the pipe is due to convection, and you have to make sure that there is sufficient length of pipe so that there is heat transport along the surface due to convection, across the surface due to conduction, in such a way that the temperature at the outlet is the desired value. In addition to this, you also have to make sure that there is sufficient pressure difference between the inlet and the outlet so that you get the desired flow rate. And then we had looked at a third example, which was the drying of droplets in a spray dryer, okay, where it is necessary to make sure that there is sufficient transport of moisture from the droplet to the ambient air okay, so that the droplet dries by the time it reaches the surface. That itself is not sufficient, you also have to supply the latent heat. Okay. And one way to do it is what is called the unit operations approach. Okay. So, let us just look at what is the unit operations approach. Okay. So, you consider this entire system as one unit and try to predict based upon the temperature differences, the concentration differences, how much transport is going to take place. Rather than looking at the transport that is taking place in the unit operations approach, what is done is to write equations for what are called the average flux. Okay. Flux of mass, for example, is mass transported per unit area per unit time. Okay. What we desire actually is to know how much mass has been transported per unit time, right. So, we want to know how much A has been converted per unit time, how much B has been produced per unit time in the reactor, for example, or how much energy, heat energy has been transferred per unit time in the case of a heat exchanger, for example. Okay. Rather than writing these in terms of the total amount transported per unit time, in unit operations these are written as the amount transported or amount converted per unit area of the surface at which transport or conversion takes place per unit time. In the case of the reactor, that surface would be the catalyst surface. So, the flux, the average flux, okay, is going to be equal to the ratio of the total conversion rate divided by the total surface area of all the catalysts particles. So, you take the total conversion and divide it by the total surface area of all the particles. You would expect that as the number of particles increases, more conversion will take place. Okay. But if you define it in terms of per unit surface area of the particles per unit time, okay, you would try to write down some kind of correlation for that average flux. Similarly, for the heat transfer problem, the correlation is written for the heat energy transported per unit area per unit time. Okay. So, you take the total heat transported per unit time divided by the total area of the pipe in order to get an average flux. Okay. You would expect that as the length of the pipe increases, the total heat transported will increase, okay, which is true. Okay. But rather than writing it that way, we express it as a flux, heat energy transported per unit area per unit time. Okay. So, if you know what is the flux, the average flux, if we have some way of predicting what is the average flux based upon all the parameters in the problem, we can then find out what is the total flux, okay, and then design the length of the reactor in such that the total energy transported per unit time is the desired value, is the design value. Okay. And similarly, in the case of the spray dryer, okay, the moisture that is transported is written as moisture transported per unit area of the droplet surface per unit time, okay, because each droplet has to dry sufficiently that there is no moisture by the time it hits the wall. Okay. So, rather than writing an equation for the total amount of moisture that is evaporated in this entire reactor, it makes more sense to write it as the flux of moisture. Is equal to mass transported per unit area into time. Okay, if we know what this is, then we just multiply by the surface area of the droplet in order to find out what is the total mass that is transported, and design the reactor or design the spray dryer, the length and the height and the radius in such a way that all of the moisture has evaporated by the time it hits the wall or the bottom of the spray dryer. Similarly, in the case of the heat transfer problem, we define the heat that is transported to the surface per unit area of the droplet per unit time. Okay. That has to be equal to the latent heat that is required for evaporation. Okay. So, these are the kinds of quantities that are used in a unit operations approach. We predict the total the average fluxes, multiply those by the relevant surface areas to get the total rates, and we design the surface areas in such a way that the rate is equal to the desired value. Okay, that the objective that we want to achieve as far as the evaporation or reaction or heat transfer is concerned. Okay. And rather than writing these fluxes, we use non-dimensionalization. We non-dimensionalize these fluxes by parameters in order to get a relation between dimensionless groups. Okay. So, in unit operations approach, we use relationships between dimensionless groups. Okay. And typically there will be one dependent dimensionless group which involves the flux, because that is what we are trying to predict. Okay. And then there will be independent dimensionless group which involve all other parameters. In the case of mass transfer, for example, the concentration difference between the surface and the bulk will be one parameter, and the material properties of the fluid will be parameters. Okay. Similarly, heat transfer, the temperature difference will be a parameter, and the thermal and the mechanical properties of the fluids will be parameters. Okay. And based upon these, we get relationships between dimensionless groups. These are called correlations. Okay. And these correlations can be derived in one of two ways. Okay. So, for example, if you want to design a big industrial spray dryer, for example, we use small scale models and derive correlations based upon those scale models for the variations in different parameters, and then use that to design the larger system. Okay. So, that is typically how we derive correlations experimentally. Okay. The other way to derive correlations is to actually solve the problem of diffusion from the surface or conduction from the surface to the surface, or momentum transfer, the forces that are exerted on the surface for known values of differences in concentration, temperature, and so on. Okay. So, correlations can be derived in one of two ways. One is the unit operations approach. Okay. That is, you just derive dimensionless groups for the average fluxes, okay, as a function of all other parameters in the problem, and then try to solve for these. Okay. So, that is one approach for that. The other approach is actually to solve for the temperature fields themselves using continuum equations. Okay. So, what I will call this first approach is what I call the unit operations approach. Okay. The second approach is what is called the continuum approach. Okay. Approach. Okay. So, for example, if I have the spray dryer example for right, and you have a droplet here, okay, and you know what is the humidity or what is the saturation humidity at the surface, okay, or you know what is the concentration of moisture at the surface, and you know what is the concentration of moisture in the ambient far away from the surface. Okay. So, you can solve the concentration diffusion equation. Okay. Concentration diffusion equation contains different components. One is the mass diffusion from the surface due to the fluctuating velocity of the molecules, and the other is the convection around the surface, because there is because this droplet is moving relative to the fluid. Okay. So, because of this relative motion between the droplet and the fluid, there can be there is a flow field that is generated around this droplet, and that results in convection. Okay. So, basically here we will assume a particular configuration, a particular velocity of the droplet relative to the ambient fluid, solve for the concentration and velocity throughout the domain. Okay. That is, we solve equations which tell us basically what is the concentration and the velocity throughout the domain of the fluid. From that we calculate what is the flux to the surface. Okay. So, here basically we are solving for the concentration, what is called a field. Okay. 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 So, in this particular droplet example, for example, okay, a field is a continuously varying function of position and of time. Okay. So, as this droplet is evaporating, the concentration varies both in position and in time. We can solve continuum equations to find out what is this variation of the concentration in position and in time. Similarly, for the velocity, we can solve equations to find out what is the variation in the velocity with position and with time. And once we have that complete information, we can then calculate the flux at the surface. Okay. And from the flux we can calculate the correlations, right, because we know everything now, we know the entire concentration field around this droplet. Okay. So, similarly in the case of the heat exchanger problem, for example, we can solve for the temperature as a function of location throughout this pipe, okay, and as a function of time. Okay. And once we know what is the temperature as a function of location and as a function of time, we can then calculate what is the flux to the surface, and from that calculate the correlation for the average flux. So, here basically we are finding out the local values of the concentration or temperature everywhere. We are then calculating what is the local value of the flux everywhere on the surface, and then averaging that local value to find out what is the average flux, and then use that, okay, to derive, and that way you will derive correlations for the average flux as a function of other parameters in the problem. Okay. So, there is the second continuum approach which we will be using in this course in order to predict what are the correlations for these different transport processes. Once you know how to do this, then you can use it for any problem. Okay. It does not have to be a spherical particle or a pipe and so on. You can solve the equations in order to find out the concentration velocity fields, and then use those known values of the concentration velocity fields in order to find out what is the flux locally at the surface, average that in order to find out the average flux. Or if you do not want to, or you can just find out what is the total transport rate if you know what is the total surface area. Okay. So, this second approach is what we will be using mostly throughout this course. Okay. Now, what are the inputs that go? So, first of all, the concentration now is a function of position, it is a function of time. Okay. It is continuously defined, that means that it is defined at each location within the fluid. Okay. So, what does it mean, a concentration defined at a particular location within the fluid? Okay. So, what it means is that okay, in 3-dimensional space, okay, if I have a particular location, right, I define the concentration as a function of the location and of time. Okay, it is a function of 3 coordinates and it is a function of time. Okay. What does it mean to say concentration at that particular point? Okay. So, what it means is that if I take a small differential volume, okay, delta V, okay, around this point, okay, if I take a small differential volume delta V around this point, right, and I find out what is the total mass within this volume delta M. Okay. So, delta M is the total mass within this differential volume, and so the ratio of delta M divided by delta V in the limit as delta V goes to 0 is what is called the concentration at that location. Okay. So, that is the definition of concentration at a particular location and at a particular time. So, let me just make that explicit here, x, y, z and t. Okay. At a microscopic level, every fluid is composed of molecules. Okay. Every fluid consists of molecules well separated in a gas, but separated by their molecular diameter in a liquid. Okay. So, if I take this location and I magnify it, right, this volume will contain a large number of molecules in it. Okay. Okay. So, the concentration basically is equal to limit as delta V goes to 0 of the mass of each molecule, okay, the mass of each molecule times the number of molecules, okay, divided by delta V. Okay. So, you count the number of molecules in this volume, take the mass of each of these, multiply the 2. Okay. In this particular case, the concentration is the molecule of one particular species, okay, and divide by delta V, and that is the value of the concentration at that particular location. Okay. So, when you do this procedure, okay, when you define the concentration at a particular location C of x, y, z, t, you are taking a small differential volume. Okay. This is equal to sum over all the sorry, this is equal to the mass of each molecule times the number of molecules divided by delta V in the limit as delta V goes to 0. Okay. Now, you have to be careful when you choose this volume delta V. Okay. Typically, if the length scale of this volume is let us say the length scale of your particle is 100 microns. Okay. This is a local volume, okay, in the vicinity of the particle, say. Okay. The volume has to be much smaller than the volume of the particle, because there are variations in concentration over a distance comparable to the diameter of the particle. Okay. So, the volume has to be much smaller than the relevant than the volume of the relevant length scale in the problem. Okay. So, the characteristic size of this volume has to be much smaller than the size of the particle, okay, so that you can get variations in concentration, okay, and you do not average over real variations, because if you make the size comparable to the particle size, okay, then you will be averaging over variations in the concentration. At the same time, the volume has to contain sufficient number of particles that you can do an averaging. Okay. If you make the volume comparable to a particle size, for example, right, if the volume is sufficiently large compared to the particle size, okay, to the molecular size, you will have a sufficiently large number of molecules in this volume in such a way that when one molecule enters or leaves this volume, this concentration does not change very much. Okay. On the other hand, if you make the volume comparable to the molecular size, you will get large fluctuations in the concentration depending upon whether a molecule is in this volume or it is not in this volume. Okay. One molecule entering or leaving this volume is going to result in a large change in the concentration. Okay. So, this differential volume cannot be comparable to the molecular size, it has to be much larger than the molecular size. Okay. So, the differential volume has to be chosen in such a way that it is much smaller than the characteristic, the size of this differential volume is much smaller than the characteristic size dimension of the configuration. Characteristic dimension, diameter of the particle, diameter of the tube. Okay. So, the size has to be much smaller than that, but it has to be much larger than the molecular scale. So, that within this volume there is sufficient number of molecules and statistical averages can be defined. Okay. So, for example, as we shall see in the case of the spray dryer, the diameter of a droplet I said was about 100 microns. The molecular size in the case of liquids is approximately the molecular diameter. Okay, which is of the order of 1 angstrom, okay, which is equal to 10 power minus 10 meters, okay, to let us say 100 angstroms, is equal to 10 power minus 8 meters. Okay. So, in liquids the molecular size is comparable to the molecular diameter, and therefore, you require that the system size should be much larger than the molecular diameter. so that you can define an intermediate scale over which continuum averages are defined, okay, in the case of liquids. Okay. In the case of gases, the microscopic scale is what is called the mean free path. Okay. In a gas, this is approximately the distance that a molecule travels before it collides with another molecule. Okay. It goes by the symbol lambda, and we will calculate it in this course. So, in a gas, the mean free path is the molecular size, and this mean free path is approximately 10 power minus 7 meters. Okay. Is approximately 10 power minus 7. To about 10 power minus 8 meters typically. Okay. So, in gases, this continuum approximation is valid so long as the system size, the characteristic dimension, is much larger than the mean free path between gases. Okay. So, if the characteristic dimension, okay, I use the symbol LC for this, okay, is much larger than the molecular dimension. Okay. Okay. If the characteristic dimension is much larger than the molecular dimension, then I can find an intermediate dimension for this differential volume delta V, okay, such that this dimension for the volume delta V is much smaller than the characteristic dimension. Therefore, I can define a concentration field over a distance comparable to this dimension for the differential volume, such that the volume itself contains a very large number of molecules, so that you can do statistical averaging and define concentration, velocity and temperature fields, okay, density and temperature fields. Okay. So, if your system size itself is comparable to the molecular dimension, then you cannot use this continuum approximation. Only if your system size is very much larger than the molecular dimensions, you can define an intermediate dimension over which you can do a balance over a differential volume and derive equations for the conservation of mass, momentum and energy. So, this is the second continuum approach. Okay. In this continuum approach, as I said, you define the concentration at a given location as by constructing a small differential volume, okay, delta V. I take the mass of each molecule times the number of molecules and divide by delta V. Okay. Limit as delta V goes to 0. Okay. This gives me the concentration at that location. Okay. As the volume becomes smaller and smaller, this ratio, the volume becomes smaller, the number of molecules in this volume also becomes smaller, in such a way that this ratio approaches a constant value, and that constant value is the value of the concentration at that location. Okay. Of course, you have to shrink the volume while keeping the size much larger than the molecular scale. Okay. Shrink the volume to a size that is much smaller than the characteristic scale while keeping it much larger than the molecular scale. Okay. And this gives me the value of the concentration at a location. Okay. Similarly, you can define the density, the mass density. Okay. For the concentration, you average only over the number of solute molecules. For the total mass density, okay, you average over all the molecules in the system. Okay. If you had only a single component system, the concentration and the mass density will be the same. If you have a multi-component system, concentration includes only one kind of molecule, the mass density includes all of the molecules. Okay. So, this is basically limit as of all the molecules Mi Ni, okay, by delta V, and this is summed over all species I. Okay. Okay. So, you sum it over all the species of all the molecules. Okay. So, that is the definition of the mass density. The momentum density, okay, is usually defined as the mass density times the average velocity, which I will define as rho times Vx, say. Okay. velocity is a vector, so it has 3 components. In this particular case, I am calculating the velocity in the x direction, say. Okay. This is going to be equal to summation over all the molecules, okay, of the mass of each molecule times the velocity of each molecule. Okay. I will just restrict attention to a single component here to make the calculation simpler. Okay. Okay. In the limit as delta V goes to 0. Okay. So, let me just spread that out. Of m times Vxi, okay, by delta V. Okay. That is the mass density. Okay. Sorry, that is the definition of the momentum density, and the velocity is basically given by taking this momentum density and dividing it by the volume. Okay. So, this I will explain this in a little further detail in the next lecture before we go on to looking at the basic equations that are used for the concentration, temperature and the momentum fields. So, I will continue this in the next half hour.